Next speaker is Siddheshwar Kundu, and he will tell us about saturation theorem for Littlewood-Richardson coefficients.
So good afternoon everyone. So the title of my talk is saturation theorem for Littlewood-Richardson coefficient. So in this talk I will talk about skew-Shur polynomial, the Littlewood-Richardson coefficient, and then the saturation theorem for this error coefficient, and then flag skew-Shur polynomial and some new results. So let's start with partition. So a partition is lambda 1, lambda 2, lambda n is a weakly decreasing sequence of non-negative integers. For example, 3, 2, 1, 0 is a partition. A partition is visualized at this Young diagram. For example, this 4, 3, 2, 1, there are 4 boxes in this first row, 3 in the second row, 2 in the third row, and 1 in the last row. And a skew shape lambda quotient mu is the set theoretic difference lambda minus mu of the Young diagram. So if we consider this 4, 3, 2, 1, quotient 2, 1, then we remove 2 boxes from the first row and then 1 boxes from the second row. The next thing is this semi-standard tableau. So a semi-standard tableau of shape lambda quotient mu is a filling of the skew diagram lambda quotient mu with the entries 1 to n, which is weakly increasing along rows and strictly increasing along columns. For example, this is a skew tableau of this skew shape 4, 3, 2, 1, quotient 2, 1, which is weakly increasing along rows and strictly increasing along columns. And the reverse reading word of a tableau T is the word R of T obtained by reading T from top to bottom and right to left. So for this tableau, reading word will come from the top row, that is 1, 1 and right to left. So first will 1, 1 come, then 3, 2, then 3, 1 and then 4. And the weight is the n tuple T1, T2, Tn, where Ti is the number of occurrences of I in R of T. So for here weight will be 3, 1, 2, 1. So see there are 3 1s in the tableau, 1, 2, 2, 3 and 1, 4. The next thing is a skew-Shur polynomial. So for a given skew shape lambda quotient mu, skew-Shur polynomial is defined as summation over all t belongs to tab lambda mu, x1 power number of 1 in t, x2 power number of 2 in t, and xn power number of t in, number of n in t. Where this tab lambda mu in is the set of all semi-standard tableau of this shape lambda quotient mu with entries less equal to n. So if we consider this particular skew shape 3, 2, quotient 1, 0, then this tab lambda mu n 2 actually contain the following 4 tableaus. Okay, so for this skew 4 tableaus, skew-Shur polynomial will be x1 square, x2 square, then x1, x2 q plus x1 q, x2, then x1 square, x2 square, which will be equal to x1, x2 into x1 plus x2 square. Now I will say what is symmetric polynomial. So let Sn be the set of all permutation on 1 to n, then a polynomial f of x1, x2, xn is said to be symmetric if f of x1, x2, xn equal to f of x sigma 1, x sigma 2 and x sigma n for all sigma belongs to Sn. For example, this skew-Shur polynomial is a symmetric polynomial. In the previous slide we have seen that this skew-Shur polynomial for this 3, 2, quotient 1, 0 is actually x1, x2 into x1 plus x2 square. So if we change x1 to x2 and x2 to x1, this would be same. So the next thing is that if we consider the set the S lambda over all partition lambda, then this is the Z basis of the ring of symmetric polynomial. And if we consider F is a polynomial in n variable, then the operator Tn of Tn acting on F defined by this bi-alternate formula will be always a symmetric polynomial. For example, if we consider this monomial x1 power lambda 1, x2 power lambda 2, xn power lambda n, and if we apply Tn on this polynomial, it will be the Shur polynomial S lambda. So now we will see what is the Littlewood-Richardson coefficient. So in the previous slide we have seen that any symmetric polynomial can be written as a Z linear combination of Shur polynomial. So S lambda is symmetric, S mu is symmetric, so their product also be symmetric. So it can be written as a Z linear combination of Shur polynomial. Then this Littlewood-Richardson coefficient C nu lambda mu is actually the multiplicity of S nu in the decomposition. So since S lambda into S mu equal to S mu into S lambda, so these two Euler coefficients are same. C nu lambda mu will be C nu mu lambda. Okay, so now if V lambda be the irreducible multiplicity of representation of GL and C corresponding to lambda, where this GL and C is the Lie algebra of all n cross n complex matrices, then this LR coefficient C nu lambda mu is actually the multiplicity of the V nu in the decomposition of the tensor product module V lambda tensor V mu. So from this result we can conclude that this LR coefficient actually non-negative. So now the next question is how to compute this LR coefficient for given lambda mu and nu. So for that we need to know what is dominant what. Say what W1, W2, Wk in 1 to n is said to be dominant if the weight of the subword W1, W2, Wt is a partition for all t between 1 and k. As an example, 1, 1, 2, 3, 2 is dominant, but 1, 2, 2, 3, 1, 2 is not dominant because the subword 1 to 2 that I mark in red, if you see the weight of this word, it is 1 to 0, which is not a partition. Now a given partition lambda 1, lambda 2, lambda n, R lambda, I define R lambda is the word 1 comes lambda 1 times, 2 comes lambda 2 times, and n comes lambda n times. As an example, R of 3 to 1 is actually 1 on 1, 2, 2 and 3. Now the thing is what is lambda dominant tableau. So a tableau T belongs to tab mu n is said to be lambda dominant if the concatenation what R lambda star RT is to be dominant. Now I can say what is how to count this coefficient. So it is called tableau model for LR coefficient. So this is the set of all tableau T such that this R lambda star RT is actually dominant what of weight nu. For example, if we consider lambda equal to mu equal to 210, then the all semi-standard tableau of this shape are actually this 8. Okay, but there are, and these words are actually this R lambda star RT. But see this word is not dominant because if we consider the subword 1, 1, 2, 2, 2, its weight will be 2, 3, 0. That is not partition, right? So this is not dominant. Similarly, this is also not dominant, and the rest of 6 is dominant. And if we consider this word, then the weight will be 4, 2 and 0. So as 4, 2, 0 will come in the decomposition. And the next is 4, 1, 1. So 1 is 4, 1, 1 will come. And the next is 3, 2, 1. And this is also 3, 2, 1. So 2 S 2, 3, 2 will come. And so on. And now this is the classical Littlewood-Richardson theorem that is for any given 3 partition lambda mu or nu, if C k nu k lambda k mu greater equal to 1 for some k greater equal to 1, then C nu lambda mu also greater equal to 1. Where k lambda means if we consider lambda is lambda 1, lambda 2, lambda n, then k lambda is k lambda 1, k lambda 2, k lambda n. Now before going to some new results, we need to understand what is flag skew tableau. So a flag phi, phi 1, phi 2, phi n is actually n tuple of non-negative integers such that 1 less equal to phi n less equal to phi 2 less equal to phi n, and the last component will be n. A tableau is a respect flag phi if every nt in the kth row is at most phi k for all k. For example, see this tableau R, this respect 1 and 2 because in the first row 1 is there and the second row maximum entry is 2. But in the As it is not respect the flag phi because in the first row there is a 2. Okay, and by this tab lambda quotient mu phi, we denote the set of all tableau of shape lambda quotient mu that respect flag phi. Now what is flag skew-Shur polynomial? So flag skew-Shur polynomial. So remember I defined skew-Shur polynomial. Then I take the summation over all tableau of this skew shape. But here for flag skew-Shur polynomial, I will take the tableau over only this flag skew tableau. Okay, and the sum over all weighted sum of the monomials. And in particular, if we take phi equal to n, all are n, then this flag skew-Shur polynomial actually skew-Shur polynomial S lambda quotient mu x1, x2, xn. And now define what is flag skew LR coefficient. So given 4 partition lambda mu, gamma nu and flag phi, this flag skew LR coefficient is defined by okay. So to define, I'll explain by this. So first consider this flag skew-Shur polynomial as mu cosine gamma x pi. Then multiply with the monomial x1 per lambda 1, x2 per lambda 1 and xn per lambda 1. Then act this polynomial by Tn. Then it will be symmetric polynomial. Any symmetric polynomial can be written as a uniquely written as a Z linear combination of Shur polynomial. Then this C nu lambda mu cosine gamma phi will the multiplicity of the S nu in the decomposition. Okay. In particular, if we consider lambda as empty partition, means all are 0 and phi is all n, then this should be the usual Euler coefficient. And the new result is the first one is done by Professor Miganda, Professor Raghavan and Professor Vishwanath, that for lambda mu nu and flag phi, if C k nu k lambda k mu phi is greater or equal to 1 for some k greater or equal to 1, then C nu lambda mu phi will also be greater or equal to 1. And the next two results are this how to count this flag skew Euler coefficient, that is the set of all flag skew tableau such that this concatenation word R lambda star R t is actually a dominant word of weight nu. And the next is the saturation theorem for this coefficient, where here it is only k mu, but here it is quotient by some skew shape gamma, that is if for all lambda mu gamma nu and flag phi, then this C k nu k lambda k mu cosine k gamma phi greater or equal to 1 for some k greater or equal to 1, then C nu lambda mu cosine gamma phi also greater or equal to 1. And there are all the references that is for a classical Euler coefficient saturation theorem, and another proof by book, and these are the Reynolds homogeneous paper where this flag skew sur polynomial comes, and these are the first result by Miganda, Professor Raghavan and Vishwanath, and this is the last one is a recent result. Thanks.